Good morning, everyone. Thank you for joining me today, at least morning where I'm at here in Colorado. Probably have attendees all over the world, so welcome and thank you for watching, no matter what time zone you're in, or maybe you're watching a recording. My name is Walt Prentice. I'm an engineer here at Applied Flow Technology. What you care about most is that, well, today I am your presenter, one and only. Today we are going to talk about gas transient analysis for process safety. Gas transients is kind of a big topic, but also a new topic, so we want to spread the knowledge out there. I'm going to focus in today, though, specifically on relief valve discharge or safety valve discharge in our new software, AFT xStream. This is a compressible flow transient solver. We'll go through dynamic forces and system responses. So strap in. It'll be a great webinar today, probably one of my favorites I've done so far. So we're going to start with some background on transient analysis just to make sure everyone's on the same page. What is it? Why you need it? How do you do it? And then we will jump into xStream, which is that compressible flow software I was talking about. In there, we will go through two examples specifically. One where we have multiple relief valves in a system, and then one where we are looking at the dynamic forces from a relief event in the steam system. These two specifically were chosen because the code, there's a paragraph in ASME B311 in the Appendix 2 talks about relief valves for power piping that, well, if you're going to have multiple relief valves in your system, so make sure to check them out and maybe turn them the other different directions so they don't interfere with one another and all that. But they don't really give you a whole lot of guidance on how to do that. They just say to do it. So that one was really what I wanted to focus on, because I thought that was pretty funny. And then, of course, more generally, you have to look at the different forces, which will lend to stress analyses and all that when you have these transient events and you don't have just the static steady state forces to worry about. All right, so transient analysis, what does this really mean? Well, it means things or parameters, in italics, vary with time. You can have a system that looks like things vary because what comes in and out of a heat exchanger are different, but that differs spatially. It differs with length, not with time. So what this means is if you took a picture of a process, then took another picture in the same spot, but just later in time, maybe an hour later or so, you will see a different value. So the opposite would be true for steady state. You can take a picture at any time, as long as it's the same spot any time of the day, and it'll always look the same. So examples of this would be valves opening or closing during the closing process, right? That's going to be transient. Finite tanks innately are transient because liquid levels will change, pressures will change. Compressor startup or shutdown, same thing would apply to pumps, of course. And then relief valves blowing off. So that's going to, again, naturally be transient because it wasn't open before and now the relief valve is open. We're going to look at what happens in between there. So this is an example system. The one actually we will work through where it has multiple valve arrangements. We're going to do, well, mostly all of this, just not compressor startup or shutdown. That we will save for another webinar, but we've got finite tanks, valve closures, and then relief valves. So again, things are varying with time. And another thing to talk about with transient analyses are that there are slow and fast transient analyses, or slow and fast transients. Well, layman's terms, slow really means just slow transients. They're about slow changes. And I specifically decided to name this, transient analyses. You can do slow analyses because you could have the same event and you look at it through the lens of a slow or fast transient. But the slow transient, or these slow transient analyses, they're like steady state snapshots, right, at different points in time. So if you have a finite tank and that liquid level is draining with time, you're not looking at how pressure waves and all of these, on the order of milliseconds, how things are changing. You're just looking at, okay, now look at it now a little bit later and the liquid level's down. So just slow over time. Fast transients, on the other hand, or fast transient analyses, it's about sudden changes and how these pressure waves propagate. Ultimately, really comes down to surge, steam hammer in this case for compressible flow, steam or gas hammer it's known as. So the idea of when you're closing a valve, you have very different system responses went through the lens of fast transients versus the lens of slow transients. So let's look at that. So there will be an example here where we're looking at pressure at the inlet of a valve while it's closing. So the difference between slow and fast transient analysis. So while a valve is closing, so again, we are looking at pressure versus time. So this is the same point in space. It's the inlet of the valve. How does that pressure change with time? Well, it's at its steady state pressure. Then you close the valve and now it's at a higher pressure. And since it's closed, it's going to be whatever that upstream pressure was, because now there's no flow, there's no frictional losses. So it's a simple ramp. It just goes up. Well, that same valve closure, though, we can look at through the lens of fast analysis. And in reality, that the closing of the valve is going to cause pressure spikes and waves to propagate. It's not just a different set point. It has effects during the change. So if you look at the two, sure, they start and they end in the same place. They start at a steady state, end at a different steady state. But what happens in between is vastly different. And xStream is going to model this changing or these fast changes with things like valve closure or relief valves, all of the things we talked about. Any transient event really is going to have wave propagation, and we want to check that out and see their magnitudes, check the forces, which relief valve is going to go off first, things like that. So that was transient. Now let's look at compressible flow, because that also is a little, so like transient is a little more tricky than steady state. Well, similarly, compressible flow is a little more tricky than incompressible, because density is a strong function of pressure. It just means you have to follow, or they follow, an equation of state. Pretty much it comes down to what we know as here in the States, usually most schools, they just call it PIV-NERT, PV equals nRT, which is just the ideal gas law. No matter what form you're looking at, you can just see that as the equation of state, and everything else will follow that behavior. But of course, you have different equation of state, which xStream will model. There's some unique phenomena because of this. So in steady state, something that's always fascinated me is that in steady state with a constant diameter pipe, velocity, volumetric flow, they will change down the length of a pipe. You don't see that in liquid. If you have the same area of pipe, the velocity is going to be the same. But in steady state, you have the conservation of mass, not the conservation of velocity or volume. So because volume is a function of pressure, pressure drops, well, your velocity changes, right? So there's a unique coupling of all of these parameters. So when something changes, something else also will change. Unlike liquids, where density is either constant or really just a function of temperature. So gases, of course, a lot squishier. They have lower densities than liquids, which means these pressure rises that you'll see from like a valve closure, they're going to be smaller in magnitude, but much more difficult to predict with traditional methods, because the pressure wave behavior is changing down that pipe with that changing velocity we talked about. The sonic velocity is changing because temperature is changing. So this wave front has, I don't want to say unpredictable behavior, because we can predict it with the math behind the software, but it makes it difficult by hand. What I would call prohibitively difficult to analyze these by any other means of software. There's condensation concerns, especially with steam systems, and then there's sonic choking concerns. Also with gas, you don't have that in liquid. So xStream will account for all of these. With condensation specifically, it won't model the slug or the phase change, but it will warn you of condensation, and you can decide for yourself how bad it is. and all that, and if you want to make changes to your system to get to avoid that. So why would you want to look at these transients? Well, first and foremost, you have to ensure your piping meets code. So we have 3 examples: B31.1, B31.3, B31.4. I'm sure you are subject to one of these. Today, we're going to focus on the B31.1, which is and specifically the non-mandatory appendix to. Non-mandatory is kind of a funny word because they still have rules and they use wording like engineers must, but regardless, it's, these are good practices to follow. 31.1 is specific to power piping. Really, a lot of it's just about steam systems. But these principles apply to everything else about your process. You want to make sure your pressure and your forces are doing okay, or your pipe material are okay, subject to those forces. So you got the code reasons, and then there are less coercive reasons that I would rather want to convince you to do these things, even if you didn't have to. Well, you would have confidence in your safety studies and in your worst case scenarios that you have to go through to make sure all bases are covered. You can test how to mitigate problems either retroactively or proactively. Retroactively, something has happened in the past. You have to figure out what the heck happened. Why did something fail? And then put in a fix. Or proactively, before anything happens, maybe on a new system where you bring in a consulting team. Proactively, so before you've caused any problems, you've decided how to, what valve closure profile should we use, things like that before it happens. You get insight into the transients as part of a network. I bolded and underlined because most transient studies are like what you'll see in code. They're really localized. They look at one specific component, but of course, it's all one system tied together. So you can't just look at one component. You have to look at how are these pressure waves changing through the whole system. And my favorite reason is, well, these studies are just plain old-fashioned fun. It's probably one of my favorite webinar I've presented so far, most likely just because it's really cool to be able to see things visually and use the software tool to do something that you just cannot do by hand. So what is xStream? It's our new software program that will model these rapid compressible transient events. The solver is based on the method of characteristics. This is just a mathematical tool to solve partial differential equations. We use the same solver in AFT Impulse. If you've ever used that, I've heard of that. That is the liquid transient solver. I can't say incompressible because even liquids are slightly compressible. In transient analyses, you can't make that assumption because then you wouldn't have a different wave propagation and all that. So it will capture this wave transmission based on wave speed and bulk velocity. Those things, again, are going to be changing down the length of the pipe, makes things a little more difficult. It will, xStream provides precise results without oversimplifying assumptions. So it will solve all the fundamental equations, mass and energy, momentum, I guess kind of spin off of that. Models the real gas effect, so it's not just an ideal gas equation of state that we use. There's the Redlich-Kwong and then some others. There is heat exchange, so it's not just assumed, isothermal. There would be heat exchange, I guess, but we don't make the assumption that things are either isothermal or adiabatic. There's no convection through pipes like you would have an arrow that is coming with this first iteration. We've just done heat exchange through heat exchangers, which you might have even caught a glimpse of when I pulled up our example system. You'll see in a bit. Okay, so let's go through that first example, multiple relief valve arrangements. So we have 2 pressure vessels in a continuous process. There is valve failure downstream and it fails closed. So it just shuts off. That is the valve we're talking about. Here's our system. Today we're looking at a hydrogen system as part of some other process, maybe ammonia production or well, really anything. But I just wanted to get an example of the process out. So what we have is delivery of hydrogen and then a recycle line of hydrogen coming back in, mixing, going through heat exchanger to preheat for whatever is downstream of this process. And there's a valve, an isolation valve that might shut off and it fails closed because for whatever reason, this specific process, if there's failure, it's best to fail closed. it's just hydrogen, so relief coming out isn't as dangerous, but you still need to do a study on it. So what happens when that valve closes? What is the relief behavior? There are certain questions we have to answer. Which relief valve is going to open first? What is the system response? That's a general question, of course, but what is happening? And how does the valve closure time impact results? Because I could slam this almost instantaneously. I could close it over a few seconds. And how does doing that change results? So let's bring up the software. So here's the interface. If you've used AFT software before, and I'm assuming most of you have, that's why you know about this webinar and why you're watching. It's very similar to other software programs we have, almost identical actually, where you have drag and drop the workspace, and then all of the windows for the input, and then output over here, and graph results. Really, we'll spend most of our time in graphs. So what's important with transient analyses, and I'm not trying to teach you how to do transient analyses necessarily, just show you that it's possible and to show you what xStream can do, but you always want to start with the steady state and see and calibrate that, make sure it matches what you expect in your process, make sure things look okay, there's not any funky results. Then you can move into the transient. And the transient here is that we have a valve, and this valve is going to start open and then close in 0.1 seconds. This is going to be our medium time, but just our first time to look at to see what happens. So that valve is closing. This heat exchanger will have to also shut off, because if you close the valve and there is no flow, but you have a constant heat rate coming in, your temperature essentially goes to infinity. So anyway, this heat exchanger has to shut down. It's part of this control system I've decided for this this process specifically. And what it is doing, and something really cool about xStream is you can get pretty intense with the control logic, that if the mass flow, let me move it back down, I'm sorry, mass flow rate is less than 0.1, I just considered that, close to 0. Pipe 2 is this 100-foot pipe right here, the outlet. So the point is, when the mass flow into the valve is nearly 0, shut off the heat exchanger, part of the control system. Okay, so when we do that, the first question was, what relief valve is going to open first? So after running the model, you can go to output and see event messages by time. And you don't know what junction 6 is, but I do. I've changed the names and all that to make it more presentable and pleasing to the eye, and just not naming things J and all that. But it still has the number. Junction 6 is actually our storage tank. And it's a legitimate question to ask what relief valve is going to open first, because it's not obvious. If you close the valve, and that's still pretty quick, 0.1 seconds, you might expect that pressure wave to propagate through and actually trigger this relief valve first. Or maybe after some, wave oscillation where it's coming back and forth, that it would trigger this. It is actually closer to the valve than the other one. This tank, well, it being a tank with a volume, it takes time to pressurize that, right? And then to open. The relief valves are set at different set points, where this one's set to blow at 125 pounds. Yes, I'm using imperial units or US units, because that's where I am. Sometimes I'll switch around, but just bear with me if these aren't your normal units. And the other one is at 115. So this was 115, 125. There's a 10-pound difference. That's pretty significant. So I guess that kind of makes sense why this one would blow first. But the point is, you don't necessarily know right off the bat. And to do a safety study, you want to know which one's going to blow first, so you can look at, do a dispersion study or see if there's toxins and how fast are they being relieved. Is that one first? Is there a blowback, or backflow? So we have found this one blows first. That's great. The next question is, what's the system response? What is happening through my whole system as that valve closes? Here we've got all of our tabular data. That's known as the output tab. And though it's always better to look at things, not always better, I guess I should say that. This is definitely condensed and all that. But what I like to look at presenting is graphs. Who doesn't love graphs? So let's have a gander at a profile. You know what, I am actually going to leave it side by side so we can look at it. So what we're looking at, these are profile graphs. Profile, meaning these are changing with length. So this is my main profile is what I'm calling it, from the storage tank all the way through to my downstream process. And the reason, so we have velocity and pressure. The reason velocity jumps up in the middle, because that's kind of odd, that's because that's where this branch is. So if we're looking just at the top profile, right where this recycle is coming in, we have a jump in velocity. Right? And then you can see a drop in pressure across my valve. And yeah, so that's what we're looking at. But we said this was transient, so this isn't just staying this way all the time. This is the initial steady state snapshot at the very beginning. We can actually play this animation so we can see what's happening. So what do we see? We see velocity dropping as the valve is closing. That makes sense. Pressure's kind of rising. Makes sense. So let's have a look when, okay, velocity is at my 0 line right at the valve, right? Right at the valve at 0. My valve has fully closed. It was a 0.1 second closure, so it makes sense that at the time it's 0.1. That is 0. What's pretty interesting is there's a velocity that's still positive that wants to go to that valve. And that's because this closure and this pressure wave hasn't communicated upstream yet. Again, we're on the order of like milliseconds, so this happens quite quickly. That is still positive, so it wants to flow this way. But the path to my storage tank is actually negative. I have backflow here. So what this means is my recycle line is now no longer just feeding my downstream process, but my flow is splitting. Which, you know, that's to be expected. With the valve closure, you're going to now have more resistance and redistribute flow a little differently. And if we keep going, eventually, all of that is negative. What negative means in our software is it's the opposite direction of these arrows. When you draw your model, you think the flow is going to be a certain way. So when it's negative, it's actually going the other way. Everything is going back towards this storage tank, but is anything coming back in this recycle line? Maybe it's shooting back up. So something I like to do is to load multiple graphs in one window. So what I'm going to do is I'm going to pull this out. Just remember this giant jump in velocity, that's my branch. And this is my recycle line. So just looking at how my recycle line varies with time, how its velocity varies with time. This bottom one is my relief lines. You can see they opened I'm sorry, I misnamed these. The tank relief is the first one, and the heat exchanger is the second one. I apologize. But in any case, we're really just looking at these two graphs. This is my profile, and then this is my recycle line, now looking with time, not length. So it's not an animated graph like this other one is. So if we keep going, or I'm sorry, start over, but look when there is all negative velocity. Okay, so everything is negative. But my recycle line is actually still positive, and so it dropped a little bit, but then it'll go back up. All of that is positive, which means everything about my recycle is going back into my storage tank. So that's why that first relief valve, or that storage tank relief valve, pops first. It's because everything starts to come in here, and that effect, that has more of an effect of pressurizing than anything down here. So it blows first, then after a little while, this one will blow in the new steady state, which we saw in this graph. The new steady state is achieved, right? Where now flow is going through both of those valves. So something powerful with AFT software is that we have scenario managers. So you can look at you can take a copy of your model, and make a tweak to it, right? And it's all in the same model file. So in this case, what the next question was does valve closure time have an effect on results? So we can just make scenarios and say, okay, well, I want to change my closure time to be much, much faster, instantaneous. And I want to make one where it's much slower. So we can make these scenarios and then compare them graphically also, which is beautiful. It's one of the new features of these latest, the latest batch of softwares, and especially with xStream being brand new. So if we go, what we would expect, let's start with that. A faster closure, that's going to cause a more dramatic pressure rise, and that will propagate through the system sooner. Things will happen a little faster, but do we see a difference in which relief valve opens first? So we can go back to our event messages, and my J6 still opens before my J7. Something of note also in these lines is that it'll warn you when something's become choked. So in this case, the relief valves open and immediately become choked. And the same was true at 0.1 seconds and will also be true at the 1 second closure. So let's go look at our graphs. So we can look at multiple scenarios in a single graph. So if I go to my relief, what is happening? Okay, this one I did name correctly. So again, my sincere apologies for any confusion, but this graph is true. So my 0.1 closure, so this was the very first scenario we looked at where the closure happens in 0.1 seconds. We have my storage tank blows first, right? Then my heat exchanger blows. So what happens when we do a fast closure? I would expect probably the same behavior, just kind of shifted in time. And in fact, that's what we have. So this is my storage tank. This is my storage tank if the closure is 0.001 seconds. It's just shifted to the left. It's just happened sooner. My steady state in the long run is still the same. So then what I expect with my heat exchanger is that it's also just shifted a little bit earlier, which is, yes, it is true. So there really wasn't that much of a change in true behavior with the relief valve specifically. And if we look at now 1 second, so it should be much longer, I would expect my storage tank to still blow first, but be much further along. And there it is. It has shifted this way, and then my heat exchanger likewise has shifted. So really all you've done is just shift the absolute time, but you haven't shifted the relative time, which is good because sometimes you don't know how your valve is going to close in your real system. So you kind of have to make some assumptions. And if everything lines up and says you're going to be okay, and there's no crazy changes in results, that's always good. So nothing's too crazy going on with the relief valves. Something that is interesting, if we look at the profile here. So here's that same profile, but now we're looking at 3 scenarios. Once again, this is our branch where velocity jumps up because now we have flow coming in. You can see that fast wave drops that velocity to 0, and then downstream of that valve, which is over here, it gets really negative. And that's just an effect of doing things so fast. You have so much overshoot and overcorrection. So you can see that velocity is dropping. You see more of a distinct wave front than you do when it's a slower closure, right? So this was our original, was the red. Blue is shows this wave front, right? It's just more dramatic is the point. Everything is more dramatic and faster. See, pressure rise obviously was much faster than the others. Something that is pretty interesting, if we do a similar thing where we can load more. Okay, I'm gonna hide that bad boy. So we just look at this. So again, our profile's over here. Here's a similar graph to what we were looking at in the original scenario, where we're looking at the velocity of the recycle line. This is the recycle line. The medium and fast closure have very similar behaviors where they drop in velocity, then shoot back up and drop. But my 1 second, my slow closure, where there wasn't really like an obvious wavefront, an obvious sudden surge, that actually increases with velocity or increases with time and then will drop down. It doesn't have this wave-like behavior. And that's a direct result of the pressure wave and the velocity changes just not being as dramatic. The system has time to settle out. The system has time to, to correct things without overshoot and overcorrection, right? It just kind of like just happens. You're changing velocity a little bit. This is an example of like a slow transient, right? Where you don't have a huge pressure wave propagation. But it's still interesting that velocity increases, and in no other scenario does that happen. Well, if we look at, I will actually just load my recycle. I gotta close this first. I'm gonna add temperature and pressure. So remember, one of the things about compressible flow is that all these parameters are tied and you follow an equation of state. So if you look at one parameter, you really have to look at two others. Velocity, temperature, and pressure are all related by that equation of state. So why does this happen and not happen when it's a slow closure? Why is this velocity increasing a little bit? And it's directly related to that pressure wave coming, because the pressure wave doesn't just go to the tank, right? The pressure wave comes back to the recycle as well. It'll branch off there. So when it's a fast valve closure, you see that pressure spike and that temperature spike. And according to our equation of state, depending on the magnitudes of those, the velocity can decrease. And then, the same thing happens when it's a medium closure. But in a slow closure, you don't have that surge of pressure or temperature. And the magnitudes of any slight changes are such that the velocity actually increases a little bit. Obviously, it's, pretty small compared to the magnitude. Magnitude's huge, 2000, probably unrealistic, but I wanted to kind of exaggerate effects here with high Mach numbers. So anyway, the point being, things are not intuitive, and it is kind of weird. Why would 1 second change my behavior so much, at least initially, and why would the others not look like that? So that's why. But if you still look in the end, it just, it takes longer to drop my velocity, which is obvious because it was a longer closure, but my steady states are all, they all go to the same steady state. So in the long run, things are the same. It's kind of like that graph I showed you before, where you can look at a slow transient or fast, and the initial and final steady state should be the same. Okay. All right. So we had our questions. Which relief valve will blow first? That is the storage tank. It's not obvious, so it requires a study. What is the system response? Well, there's backflow into the storage tank. That's what we figured out. So you have to consider this for the safety study. The backflow could have easily gone down the recycle line, but that doesn't happen. It actually goes into the storage tank. And that has to be considered as part of the safety study. Again, if you're looking at dispersion effects or toxins, and you just isolated the storage tank and looked at its own components, well, now you have backflow. So what if there was something upstream that wasn't the same fluid, and it now goes in that storage tank, right? It flows. The valves relieve the pressure and reach a new steady state. So there's no further accumulation. Looks like everything was okay. There was no clear disturbance in flow from either relief event. So as we played things through time and the relief valves went off, that didn't really change things much. The flow was actually choked at those relief valves, so it could only go so fast and cause such a disturbance, and you just didn't see that really in the system. Just, again, good. So how does valve closure time impact results? Well, it just shifts the absolute times of opening, but the behavior is still pretty much the same for relief valves. The only thing that was really different is that the recycle line behaves a little differently in that initial time period. As we looked at increasing in velocity instead of decreasing, that's just an effect of the pressure and temperature surges. So here's one of the graphs we looked at. I have it in the presentation just for you as a resource. So if you want the presentation, just let me know. I'm happy to provide this. But this is just showing a similar thing where the velocity is dropping, right? And you can pause it and see what's going on in time. Again, this was the same graph we looked at right before coming back to the slides of the 3 different scenarios. Remember, these are scenarios. So one's fast, medium, and slow closure. Okay, let's move on to the next example, which is all about dynamic forces for steam relief. So there's a steam line hooked up to a heat exchanger, the shell side. We're going to do a safety study here, or at least look at forces and all that. It's hooked up for cleaning, and it's usually closed because during process operation, that steam is not supposed to go in there. It's just used for steam blowing. Not temporary piping, but permanent, just hooked up. We are not going to model the heat exchange fluids. So this is a major assumption. We're modeling pure steam. And this is just part of the story I've come up with. Your specific process, obviously, you have to decide what is an okay assumption, what's not. But here we're looking at the shell side heat exchanger, but really only going to look at how steam rushes in. So there's a valve on the steam line that will fail open, and it will charge the heat exchanger shell side until it pressurizes and is too much and blows a relief valve. The worst case scenario with this, well, you might say, well, couldn't the steam just exit out with the other flow through the heat exchanger? Well, we're going to assume the worst case scenario is that the flow through the shell side of the heat exchanger stops. So pretty much what this means is we're just charging a tank with steam and then seeing how the relief valve comes off. But it's part of the story. So the questions to answer are, what are the dynamic forces seen by the relief system? And then are those affected by valve opening time? Because in our last example, valve closing time didn't really affect things. But in this case, how does valve opening time affect forces? So here's the system. What I was saying about the worst case scenario is truly you would have, your other gas flowing through this shell side, which could be maybe like helium or something high heat capacity. Well, we are assuming in this case that those have closed, that while this valve has opened, things close. Part of my control system, again, I am assuming, so I don't even have lines in and out, I just have the tank. The point is, steam rushes in, pressurizes, this relief valve will pop open, and then flow will suddenly surge through my discharge piping into my discharge header. And you will notice, maybe even call me out and say, well, that doesn't look like a relief valve, that looks like a manual valve. Relief valves in xStream assume discharging to atmosphere or to an open system. And in order to discharge to a closed system where forces really are major, you have to use a manual valve, but it works all the same, and I'll show you that. So here are the questions again. Okay, so let's pull it up. Since we're looking at forces, and the reason you would care about that typically is to export those to then do pipe stress analyses. So load your force files into your pipe stress program. That is all going to be three-dimensional. So here I've drawn an isometric view of our system, and I have a coordinate system according to my pipe stress program. Because in AFT, it doesn't matter. AFT looks at things axially, like it's just flowing through the pipe in one direction, right? It doesn't care in reality if it's X, Y, or Z, it's just flowing down the pipe. But in pipe stress, it does matter. And you can actually account for this in AFT xStream or AFT impulse, these directional effects. So if I have my coordinate system from my pipe stress program, I can set up forces with unit vectors to account for this. So this relief valve, again, is a manual valve. It looks like a normal valve you've seen. But like we saw before, these things can have pretty sophisticated control systems, much more sophisticated than what I have here. But at least here, it will show what it can do. And similarly to what we saw before with the heat exchangers, this is tied to a single event, meaning this valve, what do we see? This valve will open really, really quickly when the pressure in my pipe, my inlet pipe here, the inlet of my inlet pipe, so really right on top of the tank, is greater than 125 pounds. It will blow off and then suddenly surge everything with pressure and flow. So the forces we are going to look at would be this pipe, this one, this one, and this one. So all of the discharge, there's 4 total. So if we are setting up our system, again, I'm not going to really show you how, because that's not the point. It's just showing you that you can. that we can set up all these forces. So that's pipe 4, 5, 6, and then 7 was down here. Set all of these up with my unit vectors according to how my direction of flow is different or aligning with my coordinate system. And I've chosen these force types for a reason. So if you have questions, why would you choose these specific types? Just let me know. And I don't want to go too into depth on how to do things, just that you can and what it looks like to do it. So when we, the initiating event, that was the relief valve. The initiating event is that this valve fails open. So it will open just with time, not tied to anything else. It will open in 2.2 seconds. This opening time doesn't really matter because it will just shift the absolute time like we saw in the other example, where it'll just charge the tank, you know, a little slower or a little faster, but the relief is all the same because that is a sudden relief. So I've done multiple steady state scenarios to make sure things are reasonable. That's always first and foremost. Now we get into the transient. And I'm really only looking at 2 different scenarios, fast and slow relief. Fast relief is just it pops open and things rush in. Slow relief is, well, it slowly opens over time, right? What we expect is that fast relief has more dramatic effects and more dramatic forces, you would think. Let's see if that's true. So this is the fast relief again. And I know, well, according here, my relief valve opened at 2.25 seconds. So it took a couple seconds for it to charge, and then it'll blow open. So I can actually fast forward to that point, 2.24, and then play my animation again. Okay, so this is the profile. This is the profile post relief. So it's all 4 of these pipes, and these junction markers on my graph correspond. J4 is my relief valve, J5 is that branch, J6, really long pipe, right? Then J7, and then J8 is my my discharge boundary condition, discharge header. So that's what those markers are. And if we play this, okay, it opens, right? The relief valve opens. You see a sudden wavefront of pressure moving through my system. Whoops, right? Sudden surge of mass flow moving through my system. So you can see that happening, and this steep nature of this wave, that's because it's such a fast relief. It's so instantaneous that this pressure wave is just moving through very quickly. Cool, so that all makes sense. It's not unintuitive there. That's great. So let's look at those 4 sets that I had up. Let's look at just one of them, pipe 4. So this was right off the relief valve into to another elbow or that branch. You see that impulse. Why is it so high and why is it so short-lived? So similarly, what we were doing with the other example is I want to load multiple graphs so I can track along. Okay, so I'm going to get rid of this to make sure it's not as gross. Okay. Oh, sorry, glitched out for a second. There we go. So forces all come from, well, dynamic forces. This force imbalance comes from these transients and pressure differences inlet and outlet. So if we take it back a few time steps, right now you can't quite see, but it's about 0 force. If I go back even further, it's a little more obvious. There's no force. There's no net force on this pipe. That is because the pressure in and out are the same, and there's no flow, so there's no frictional effects to take into account. But when that pressure wave comes through, the end of the pipe hasn't seen it yet. Again, we are on the order of magnitude milliseconds. So there's truly an imbalance, and a pretty significant one, even though it's only maybe a 5-pound pressure rise. The force resulting from that can be pretty major. I mean, everything's relative, so maybe 150 isn't that major to you, but it is major relatively to other cases. So because that wavefront is so steep, the inlet and outlet see such a difference, right? And then the wave, what you'll see is the wave comes back and comes back through, and then you see the second spikes that are much smaller. Frictional effects have dampened out the wave. So now if we moved into pipe 5, well, our wave's already there. So similarly, right, we're at 0, and then my wave comes through, and yep, the end of that pipe, now a new pipe, hasn't seen the pressure rise, but the beginning starts to, right? So these forces, the size and the magnitude of these forces really are about this wave front. Does this wave front fit inside of the pipe? This is sometimes called a characteristic length of the wavefront. As long as that is smaller than my pipe length, then I'm going to get very dramatic forces. So if we keep moving forward and look at my very big pipe, number one is you're not just going to see it so short-lived. It's not going to be just a blip and go back down. It's going to be extended because that wavefront is fitting in there this whole time. So what you'll see here is a much longer, again, longer being relative because we're still on the order of milliseconds, but a much longer sustained force, and then it comes back really quickly because it's right at that boundary condition, it comes back. So if we look at the, I'm just going to go ahead and load my multiple scenario because we were looking at fast and now slow is another point. Okay, so we looked at fast relief in this. I'm going to kind of hide off this force for a second, but leave it there. So my slow relief, though, let's see, is I think it opens in 0.5 seconds. Let me check my output, though, to make sure I can go to that scenario. So it's, sorry, it still opens at 2.25. That's great. But this is opening in 0.5. So the relief still starts at the same time, but it's now more of a process than an instantaneous thing. So I can reload these back up. Doesn't matter what scenario I'm in since it tracks both. Okay, I'm gonna hide this. All right, so we're looking at slow. So if we fast forward again, I'm gonna kind of speed it up. Yeah, why not? I mean, I'm moving my animation faster and it's still, this pressure wave is so slow. It's like not even a pressure wave. It's not even a wavefront. It's more behaving like a slow transient. So what is that effect on forces? So I want to look at, yeah, just my slow relief. So if we go back, to when the relief valve opens, there's just a tiny little blip of a force because the imbalance now is just not so significant. There is technically still a pressure wave, but you don't see it. It's not distinct. And that's why I started with the fast opening, because it's a little easier to see how forces work when it's fast. You can see that wavefront. And here, well, you can see there really isn't one. It just kind of like slowly opens. The system corrects itself, gets to equilibrium faster. There's not imbalances. And you will see that behavior with all of my forces. Pipe 6 is a unique one, so I will show that a bit later. But pretty much when you compare any of these scenarios, the faster opening is going to have much greater forces. This one has sustained over, has a steady state not at 0 because it's at an exit, it's at a boundary condition. So all of that mass flow is just blowing out and causing a force imbalance and moving it upward. So you'll actually see these reach the same steady state that's not 0. And that's because at the end of the day, the mass flow outlet, at the end of the boundary condition it's still the same. It's just what happens in between that's a little different. So what is unique though is pipe 6. Pipe 6 is actually much larger. I mean, comparatively, like to pipe 4 or 5, has larger forces. Still not as large as when it's fast, a fast relief, but large enough to catch our attention. So why is that happening? Again, that's a result. let's go back. To the beginning. Oh, come on. Give me some slack here. Sometimes you got to reset things. Or not. I guess it's not going to behave right now. So I will have to fast forward. All right. Whew. Straight busting through this. Well, you can imagine when the force is 0, right? Everything's flat just like before. And as that pressure wave comes through, it more so than any other pipe, it fits better in the long pipe. And that's because the characteristic length is so big. It's because the opening was such a long time that there wasn't a sudden pressure surge that that characteristic length is still long. But it still fits. I'm doing quotes and you can't even see me, but I'm saying fits just because that's how I think of it. It fits inside this long pipe better. So that's why out of any one of these, this is going to be the largest force. The difference exit is it's still larger than that. It's a little different story just because now you're at a boundary and that force is just blowing that opening completely out. But it's still larger in magnitude than that. So again, it's about that pipe length. So here, valve closure makes a huge difference, or valve opening, sorry, makes a huge difference in my system responses as far as forces go. So let's look at, I want to look at a new graph with pressure. Okay. So what I want to show the max. What is pretty interesting here, I'm going to take off my statics. I just want to, so this is a stagnant line. Like this line will not move because it's a maximum line. Through my whole simulation, what is the maximum pressures I see with either case? Very slow or very fast. These are extreme differences. And the maximum pressures are really not that different. 4 pounds, I don't want to downplay that because that could be, pretty decent. But at first glance, you say, those really aren't that different. I mean, I can see why a faster opening would have a higher pressure rise. It's just more extreme, but everything else about the system is pretty much the same. So is it really, that much of a concern what my valve opening time is? And the answer is yes, because of forces. So here was my force definition again, more as just a resource for after the presentation, if you want to go back and check, what I did and why I did things. We had 2 questions to answer. What are the dynamic forces seen by the release system? The highest force is seen in the longest pipe. The wavefront can fit in that, right? It is sensitive to valve closure time though, so that answers my second question. Let's go back into the software though real quick. I forgot to show you, you can actually export these forces and these force sets for your stress analyses in another stress program. I brought that up, but I didn't show you. You can go to File, when you're in an Output tab, go to File, Export Force File, and you can, export these dynamic forces. These are not static, these are dynamic transient force imbalances from transient specifically, but it's still force information. You can load that into your pipe stress software and do your stress analysis to make sure your material's okay, you meet in code, all of that. So you can export the force output for pipe stress analyses, right? So that's what those forces look like. Does valve opening time affect forces? Yes, a lot, exclamation points, for the reasons we explained. Faster opening, more sudden pressure wave. The wavefront more readily causes transient discrepancies between the inlet and outlet. In other words, it fits inside of the pipe. That leads to higher forces. Even if things like maximum pressures are similar, forces can be very different. And that is a major point to highlight. And it's all about that wavefront. So here, similarly to what I did with the other example, is I have a recording of one of our graphs moving through time, just as a reference for you. So I tried to start it close to when it's opening. And this specifically, I'm looking at pipe 4. You'll notice nothing else is checked. So all the pressures moving through these, you're not going to see the forces. You'll just see from J4 to J5. But the point is, you can see that wavefront move through, and how your force, that's where you see the force, right? So again, more of a resource after the fact. More resources to keep you sharp. Oh man, that means we're at the end of the webinar. Well, we have a great tips and tricks blog on our website. If you go to the menu Learning Center, tips and tricks. The reason is, well, if you're confused, guaranteed someone else has, most likely someone at AFT specifically has been confused, and that's why we decided to write a blog on it. We have more webinars also in that Learning Center area, upcoming, and you can watch recorded ones, so ones that we've given in the past, great content, especially for transient modeling. These more tricky topics, such as like compressible flow analysis or transient modeling, you just need a little longer form content to be able to grasp. And that's why webinars, I think especially, are useful for that. Of course, they are useful for steady state and general software use. I have done several webinars on that. That's great, and people love it. But especially if you're doing transient, given today's topic, webinars are going to be great for you. We have a help file inside of the software. So there's a help button and a help file that truly actually is good. I know a lot of people are scared to use help files. I personally am for software, but if you go search in that help file, you will most likely find the answer for any question you have. Of course, you can reach out to support as well, which here is our contact info. If you have any questions on your model or about the software, support or sales, depending on the nature of your question. My personal contact info is here, waltprince@aft.com. If you want to give me a call, just same numbers, just the office, just ask for me. So thank you guys so much for your time. I will answer any questions after we close out here. I will respond by email. It was just too long to be able to answer the questions during the webinar. And if you have any questions after the fact, please let me know. So thank you again, and happy engineering. And hopefully now you can walk away with more knowledge about compressible flow transients.